In this video, we'll look at differentials for multivariable functions and estimating the range of a projectile. We're going to study the formula x equal v squared sine 2 theta over g. This formula gives the range x of a projectile launched from the ground, that is at zero height, where v is the velocity and theta is the initial launch angle and g is the acceleration due to gravity. So I can also refer to this formula as a function, and I can talk about it as a function of two variables, v and theta. Now, of course, when I say velocity, in this case, I could also be calling it the speed. So sometimes it's just convenient to switch back and forth and not be so precise. And really, the velocity here is just the speed of the projectile, and it's actually the initial speed. Theta is the initial launch angle, and that could be measured in degrees or in radians. And in this video, I'm going to use a acceleration due to gravity 9.8 meters per second squared. So if I use that, make that assumption that g is 9.8 meters per second squared, then all of the work that I'm going to do through the rest of the video will assume x, the range, is measured in meters, that the velocity, or really technically the speed, or the initial speed, is meters per second, and of course the angle could be measured in radians or degrees. That doesn't matter. At least it doesn't matter in the way that I have the function written here, as long as you recognize whether you're in degrees or in radians. When you do the calculation, you could use either one. One of the points of this video later on is there's this subtle point in the calculation where I actually have to use radians in the calculation. I'll get to that later, but that's one of the things that I want to try to get across here, is that that point where you recognize where most of the time I can switch back and forth, and I'll do that, but there's one instance where I have to be really careful. Radians is required. So we're studying this function of two variables, and also another thing that maybe point out just sort of in general, if I look at x as being the range of the projectile, it's the distance that this projectile will travel when you launch from the ground. That's specifically what this formula is derived from, the assumption that you're launching from the ground with some initial angle, some initial speed, acceleration due to gravity, no air resistance included here. So we might put v for the magnitude of this vector. It's the initial speed, and there is a height that the projectile will reach that is not explicit in this formula. We can't determine the height. This formula says nothing about the height. It tells me just that range that the projectile will travel in meters. So some examples that we could consider: what if we started with 20 meters per second for our velocity and 45 degrees for the initial launch angle? So plugging that into the function, I have sine of 2 times 45, and that's sine of 90. The sine of 90 gives me 1. So this is 20 squared times 1 over 9.8. That gives me 40.82, which means that 40.82 meters is the range. Now it's kind of funny that the range of the projectile is the range value of the function. This function, I'm using the word range in two different senses, right? They're domain values of v and theta. So x is the range value in the sense of the function producing an output, but it also represents the range in the other sense of that word, which is the distance that the object travels. Another little technical detail here that was worth just making a comment about is that it was really kind of arbitrary as to which one of these I put first, or what order I use for these coordinates of the domain values. I could have done it either way, and I just happened to choose v comma theta, and so once I've defined it that way, I need to be careful about following that particular order. Like down here, when I put in 20, 45, the first component has to be the speed, and the second one is understood to be the angle, and then you can interpret it. And so another comment is how I could also do pi over 4 and recognize pi over 4 because it's in the second component, that's why I know this is interpreted as an angle for this particular function. And at pi over 4, of course, that's the same thing as 45 degrees. And so when you plug in pi over 4, you have the sine of 2 times pi over 4. That gives me the sine of pi over 2. And the sine of pi over 2 is going to give me 1. Okay, and I'll make one additional comment here that actually, as I wrote it here at the top of the page, this is really a function of 3 variables, v, theta, and g, potentially. But if I choose g to be a constant, acceleration due to gravity near the surface of the Earth, if that g isn't going to change in this analysis, we could just switch that to write in 9.8. Another option, of course, is that this g could be assumed at 32 feet per second squared. If I used 32, I could just write a 32 here, and then everything would be measured, the velocity would be measured in feet per second. The angle would still be either degrees or radians if we had chosen 32 as our acceleration due to gravity. But anyway, the point is here that g is a constant, and so this is really going to, from here on out, going to be a function of 2 variables, just the v and the theta. All right, so how about to become a little more familiar with this function of 2 variables, let's plug in some other inputs. Let's go with 20 meters per second and pi over 2 for the angle. So the speed's still 20, so that's 20 squared, sine. Now we're going to do 2 times pi over 2 divided by that constant 9.8. This is the sine of pi, the 2's cancel. The sine of pi is 0, so we're getting 0 meters as the range. And that's because at pi over 2 you're looking at a launch angle of 90 degrees, straight up in the air. So it would go straight up in the air, come straight back down, and have no range at all. It didn't go any horizontal range, right? So 0 is the horizontal range, that's the value of x. One other calculation, let's plug in 30 for the speed and 45 for the launch angle. So that's the sine of 90, and that's 1. So that's 900 over 9.8, about 91.8. So we would expect the range to be 91.8 meters. So I'll show you what I entered into Mathematica. It would be very similar on Wolfram Alpha. Wolfram Alpha is running on Mathematica, based on Mathematica. So it's the plot of the 3-dimensional function where x is the horizontal range. I've got this 1 over 9.8 factor times the velocity squared times the sine of 2 times the angle theta. You see I have a interval for the velocity of 0 to 30 and an interval for the angle theta from 0 to pi over 2. So here's the 0 to pi over 2. Pi over 2 is about 1.57, right about here. And horizontal range is this vertical scale in the graph, and then the speed is from 0 to 30. So this is the image that we get for that surface. So that's it. That's the function that x is the horizontal range, v is the initial speed, theta is the initial launch angle, and this is a surface that represents this function of 2 variables. Here I have the horizontal range value, x, which is actually a sort of vertical axis that represents the output of the function. This is the speed, this axis here, going from 0 meters per second up to 30 meters per second. And this is the angle theta along this axis, going from 0 to 1.5. This is pi over 2 here. Right about here is pi over 4. So pi over 4, when you plug in pi over 4, you get pi over 2. And it's pi over 4 that's the 45-degree angle. At that 45-degree angle is where I get the maximum possible horizontal range. You can see that this makes sense. If you plug in 45 into this function, you have 2 times 45, which is 90. The sine of 90 is 1. And so it's when this fraction is at its maximum value of 1 that you get the maximum horizontal range. The higher velocity, the bigger the range, the further the range, the horizontal range will be with the bigger and bigger velocity. But as far as the changes with respect to the launch angle, when it's at 45, that's when this factor is equal to 1 and we get the biggest horizontal range with changes in the launch angle. So that's why the surface is peaking right there at 45 degrees, or pi over 4 radians. Okay, so here I've chosen to highlight a few points on the surface. For example, at 20 meters per second, launch angle pi over 4, we get a horizontal range of 40.8. Another point sort of back here on the back of the surface, initial speed of 20 meters per second, but launch angle of pi over 4. That launch angle pi over 2. When the launch angle is pi over 2, you're at 90 degrees, you're going to get 0 for the horizontal range. So you get that point that's sort of back there, right at 0 for the range, 0 on the x scale. Another point that's identified here is initial speed of 30 meters per second, launch angle pi over 4, or 45 degrees, and that produces a horizontal range of 91.8 meters. So let's try some of these out. I found this really fun website, phet.colorado.edu, that gives us a simulation for projectile motion. Okay, so now I'm running that program on that website. And one thing that I'll do is start with a initial height of 0. We're launching from the ground. And let's say this, I can change my launch angle. Let's put it at 45 here. This guy maybe is there just to give us a sort of sense of scale. Can't move him. I can move my target here to whatever horizontal range I might be looking for. You can also choose to launch different things, but all of these will follow the same path in the calculation that we do, because the formula that I'm using doesn't include anything about the air resistance, and so there won't be any. It won't distinguish. It'll give us the same range, whether we're doing the cannonball or the pumpkin, the human, car, any of them. So if I set the speed at 20 meters per second, I expect the range to be about 40.8. So I need to zoom out a little bit. So if our formula is correct and our calculations are correct, this will hit the target. So let's try it. So there it is, 3 stars. We got it right on the target. Let's try the piano. Same exact path. Some of the other points that I found with this are 30 meters per second and pi over 4, and I got 91.8. Let's try that. So I'm going to have to zoom out a little bit more. Okay, so now I have this at 91.7. I just couldn't back and forth, and I just could not get it to sit right at 91.8, but this is a whole entire car, so this doesn't seem like that even really matters. Okay, so then push this all the way to the max at 30 meters per second, 45 degree launch angle. Let's go. There goes the car. And yep, that's right on target. Good. So our calculations are correct. Oh yeah, another one. Let's look at shooting straight up. So let's say we have a launch angle of pi over 2, 90 degrees. I've got 20 meters per second, 90 degree launch angle. I'm going to go with the piano. Let's see what happens. Straight up in the air, straight back down, 0 horizontal range. Okay, that's not surprising. Alright, so I put all this time into playing around with this program and looking at that surface that actually like a whole nother purpose for this video that I haven't even got to yet. So let's go back to this 45 degrees, 20 meters per second, range of 40.8. shooting out the human, and perfect, he landed right there on the target. Now, the next thing that I'm going to look at is how we could approximate changes. We could study that surface and approximate changes in both the velocity and the launch angle, and how that propagates to changes in the horizontal range. So basically that brings us to these two questions here. Find a formula for the total differential in x, and use the formula to estimate the change in the range when the velocity is at 20 meters per second, the launch angle at 45 degrees. Let's put a differential in the velocity of plus or minus 5 meters per second, and a differential in the launch angle plus or minus 1 degree. So to answer part A, what is the total differential? And I mean the total differential in x. Let's just back up and say, what is a total differential in any function? So if we had a function of two variables, f of x and y, the total differential in f represents the change in the function f that's based on the rates of change of that function with respect to the two independent variables. So that is the partial of f with respect to x times some differential or change in x, and a partial of f with respect to y times some differential in y. Might be good to also see how this could be written other ways. We could say z is the range value of some function of x and y, and so this could also be written, the differential in z is, and just to demonstrate other forms, other notations for this, we could say a partial of f with respect to x times the differential in x, and a partial derivative of f with respect to y times the differential in y. And also, just for one other way that it could be written, let's say it's just the partial of z with respect to x and times the differential in x, and a partial of z with respect to y times the differential in y. So this is called the total differential in z. I think maybe I could say one other sort of maybe helpful, useful thing about what you're looking at here. That z with respect to x is a slope of a tangent. It is a rise over run. It's the rise in the z dimension with respect to changes in x. So if you look at that rise over run times this differential in x, you're actually getting the change. You're just getting so basically a rise, which of course could be negative, but it's the change in the z value based on some incremental change in x and the rate at which the z is changing with respect to x at a particular point. And also, and this is why the term total differential, this is to account for any of the dimensions in which z is measured. So if it also changes with respect to y, you could look at the rise over run in the y dimension of the z value and then multiply by this incremental change in y. Basically, it's rise over run times run. So you just get rise. Of course, the rise could be negative, and but it's the net contribution of those two terms that represent sort of a rise, a change in the z scale based on these linear rates of change at these instantaneous linear rates of change. The slopes of the tangents in each of these directions multiplied by those incremental changes in x and y give me the total differential in z. All right. Hopefully that made some sense. let's go on. So if I apply that in this particular function, the total differential in x would be the partial derivative of x with respect to v times the differential in v plus the partial derivative of x with respect to theta times that differential in theta. So when I do the partial derivatives, I'm holding any other variable as a constant. So the partial derivative of x with respect to v means that I'm taking a derivative with respect to v, the sine 2 theta, and of course the 9.8. These are all constants. So we just get 2 times v as the derivative with respect to v times the constant sine 2 theta and the constant 9.8. These are constant factors that just get multiplied times the derivative. And then I just copy this differential in v as part of the total differential. When I take a derivative with respect to theta, v squared now is a constant, and of course 9.8 is a constant, so I just copy those as a constant factor, take a derivative with respect to theta, and I get cos 2 theta times 2 from the chain rule, and then times the differential in theta, because that's just part of the form of the total differential. So if I simplify, cancel the 2 with the 9.8, and cancel this 2 with this 9.8, I come up with a form like this. Now, ordinarily, I would not leave an answer with a decimal in a fraction. That is not simplified. But under the circumstances that the 9.8 and the 4.9, they actually sort of have some kind of meaning that came from that constant acceleration due to gravity, that I feel like it's meaningful to leave it in this form, useful to track where that 9.8 goes. So I decided to just leave it there in this very rare situation where I didn't simplify this fraction. And so then I want to move on to look at what happens if the velocity is 20 meters per second and the angle is 45 degrees, or of course you could also write pi over 4. Well, we are also given differential in the velocity of 5 meters per second, plus or minus 5 meters per second, and a differential in the angle of plus or minus 1 degree. So when I plug those in, let's see what our total differential in x turns out to be. I'm going to redo the calculation so I can talk through it a little bit better here. So we need the formula, and it's right there. 1 over 4.9, velocity was 20, sine of 2 times the angle, and the angle is 45 degrees. And that's times the differential in the velocity, which is plus or minus 5 meters per second. It's like I'm going to do the calculation. By writing this, I'm just doing the calculation twice, so once with a plus and once with a minus. Then plus 1 over 4.9. The velocity was 20. Cosine of 2 times the angle is 45 degrees. And the differential in the angle is plus or minus 1. But this is where I actually have to convert the differential into radians, which I have done here. So this is plus or minus pi over 180. And so it's kind of ironic that I'm trying to make a big deal about how I have to change the angle into radians, when it actually doesn't matter at all in the particular example that I chose. Because this is going to be cosine of 90, and the cosine of 90 is 0, and this whole term is going to just disappear. But, you know, it isn't always a launch angle of 45 degrees. In any other launch angle, you're going to get some number here that you're going to have to, you know, multiply by this differential in theta, and so that'll contribute some to the change in the range. I think it's worth taking a minute to look at the units. That's part of what I wanted to accomplish here. So let's make sure these units are right. This is 1 over the units of this 4.9. They came from the acceleration due to gravity. This is meters per second squared here in the denominator. This 20 was meters per second. So the units are meters per second. The sine of 90, that's dimensionless. It actually is a 1. And this is meters per second. Let's look at the units for this one. This is meters per second squared in the denominator. This is meters per second, and it's being squared, or squaring the velocity. And then, actually, this is the cosine of 90. So yeah, I know this is 0, but it's dimensionless anyway. If it could have been any number. This has to be dimensionless as well. I'm going to write radians. It's a dimensionless measure of angle, and maybe let's proceed like that. So let's complete our dimensional analysis here. If you flip this fraction, this is seconds squared over meters times. This is meters per second times. This is meters per second. And what do we get? Seconds squared are going to cancel with the seconds times seconds, and the meters are going to cancel with meters. And so in this term, I get meters, which is the change in the horizontal range measured in meters. Perfect. That's exactly what it's supposed to be. And plus, let's look over here what the units would be. Once again, this is acceleration in the denominator, so we can flip, go seconds squared per meter. If you flip that fraction times, this is meters squared over seconds squared when you square that velocity. This is dimensionless, and this is radians. And so what happens? The seconds squared is going to cancel out. Meters cancels with this meter squared. So this is meters. So it's meters times radians, but that radian is a purely dimensionless unit of angle. And if we had used any angle in degrees, that isn't dimensionless. Degrees isn't dimensionless, and it would produce a unit that isn't correct. We would have meters degrees, and that's going to give you a wrong answer. So with any other angle besides 45, this differential in theta, because we're multiplying it by this rate of change of the function with respect to changes in the angle, we have to measure that angle in radians, measure that change in angle, measure that differential in angle in radians to get the answer right. And ironically, it doesn't matter in this example because it's 0 anyway. Okay, so that's all correct dimensional analysis. Let's go back and actually do the numbers. Sine of 90 is 1. This is 20 times 5. That's 100. 100 over 4.9 is 20.4. 20.4 meters plus, and of course this is the cosine of 90, and so this all goes to 0. And oh, I'm sorry, I had a plus or minus here, so I did the calculation once with a plus. I also am doing it with a minus. I'm getting plus or minus 20 plus 0, so plus or minus 20.4 meters as the estimate of the differential in the range with plus or minus 5 meters per second differential in the velocity. So we could expect the range to go 20 meters further or less in range as a result of this change in the velocity. Now, I chose 45 because it's also pretty interesting. How come this goes to 0? Doesn't it seem like changing the angle? You would expect changing the angle to change the range. In fact, I even know that at 45 I'm getting the maximum possible range for the projectile at 45. So any other angle should absolutely decrease the range. So how come that doesn't happen? So that's another part of why I chose the 45 as particularly interesting. And so let's pursue that a little bit further. But maybe we can take the result that we have so far and just look at that in our simulation. So at 45 degrees, it goes 40.8. Now, if we change the velocity to 25 meters per second, it's going to go about 20 meters further. Let's see if that happens. So, yep, he's a little bit further out there. Let's take this tape measure, and the way this works is I want to try to line it up. See, it's already measuring 1 meter, so I'm going to try to put it about there and say that's a distance of 1 meter. And I'm going to measure how far did he go, and I get about 63.5 meters. So that is about 23 meters further. My estimate was about 20.4 meters, and so that differential is only an estimate based on the rate of change of the surface at that particular point. This is a curved surface, and so the actual change in the range that it results from that extra 5 meters per second is a little bit further. It's actually 23.5, and so we could study the surface and see why that is. Let's go back to my Right, so if I drop the speed by 5 meters per second, what's going to happen? Well, it should be about 20 meters, 20.4, that's an estimate, for the change in the corresponding range of the projectile. So let's go from the 20, let's drop it back 5, to go to 15 meters per second, and see what happens. So measuring that distance, about 22, so maybe roughly a difference of 18 actual meters less range, a difference of about 18 here, is the actual change in the horizontal range that results from a decrease of 5 meters per second. But that's close to what this calculation is predicting based on the linear rate of change. That's what's happening with this total differential. It's giving me an estimate for changes in the surface based on linear rates of change at a particular point. Okay, so to look a little closer at what's going on, understanding the concepts of differentials a little better, I've graphed both the function. This is the surface that we were studying before, and I've also plotted along with it the tangent plane at the particular point that we were looking at. This point with 20 meters per second and a launch angle of 45 degrees and a range of 40.8. That's this point right here. So you can see a tangent plane to the surface as a result. So here you see the surface and the tangent plane at this point, 20 meters per second, 45 degree launch angle, 40.8 as the horizontal range that results. And so in this way you could see how increasing the velocity according to the tangent plane we'll get an estimate for what the surface actually does. It is the actual function that's actually increasing a little bit more than the actual tangent plane. And you can also see how changing the angle along this line, there is no increase in the x value at all when you are on the tangent plane with the particular angle and velocity that I chose. Changes in the angle don't produce any increase in the horizontal range. Here's another picture where you could see my point right there. And you could maybe see just a little bit of an increase in the actual horizontal range as you go to maybe 25 meters per second for the velocity, where that's only estimated by this tangent line. The tangent plane has the slope it has the rate of increase in the horizontal range with respect to the increase in the velocity. And I could even talk about a rise over run. We could actually visualize it like this. There's some differential in v, some change in the velocity that we actually know in this case because it's given as a actual change in velocity. Let's just visualize the positive 5 first in this direction. That is increasing the velocity by 5 meters per second. I can then figure out what is the rate at which the horizontal line changes, horizontal range changes, and that's exactly what this partial derivative is telling me, the differential in x with respect to increase in the velocity, so that I can actually compute what the actual change in the range is that comes from this term. Essentially, I'm just multiplying this differential in v over on the other side and getting a term that is part of the total change in x. And it turns out that's the only change in x comes from just that increase in v, because in the other dimension, as we change the angle, there is no change in the x because this happens to be a maximum of the surface with respect to increases or changes, positive or negative, in the angle. It's along this line. along this line, that there is no change in the x value as we follow the tangent plane along this line. What we're saying is the derivative of x with respect to theta is 0. It's because that derivative is 0 because it happened to be a maximum of the surface that any change in the angle doesn't get picked up at that particular point. Because that point, 45 degrees, is the angle at which we can maximize the horizontal range for a given speed. All right, well, I'm about to wrap it up with this video, but I thought I would just leave one sort of challenge here that I could maybe answer in another video. In order to get that tangent plane to be visualized here, I typed in the surface in a slightly different way, and I included the equation of the tangent plane. So understanding the math behind finding equations of tangent planes, I wonder if you can, I'll leave it as a challenge to see if you can find this equation of this tangent plane for this surface at the point like this. Find the equation of the tangent plane to the surface given by x equal v squared sine 2 theta over 9.8 at the point 20 pi over 4 and 40.8. That tangent plane is x minus 4.08 v plus 40.8 equals 0 in this v theta x coordinate system. So if you could figure out how to get that equation of the tangent plane, that's a nice little challenge, and maybe I'll do that in another video. Okay, so I'll stop there. Hopefully it was a interesting and helpful video. Thank you for watching.